Euclid is beginning to show that the universe we see is only a small part of the real cosmic story. Across millions of galaxies, it is tracing the hidden matter that shapes space and the dark energy that drives cosmic expansion. Tonight, this journey follows how one telescope is starting to map the invisible structure of reality itself. If this kind of calm space documentary is for you, please like the video, subscribe to the channel, and stay with the story. At the widest scale that observation can hold in a single idea, the universe does not appear as a smooth and even sea. It shows a pattern. Across immense reaches of space, galaxies gather along long strands and broad walls, while other regions remain comparatively sparse. Dense knots form where many strands meet. Vast hollows open between them. This grand arrangement is often called the cosmic web. The term describes the overall pattern of matter on the largest scales known, where the visible parts of the universe reveal a shape that is neither random nor uniform, but organized by gravity over deep time. Euclid begins its work in this outermost region of understanding. It looks not first at one galaxy or one cluster, but at the broad map in which all such systems sit. Its scientific purpose concerns dark matter and dark energy. Yet at the largest scale, those hidden components are not approached as isolated objects. They are approached through form. The universe carries a record of its contents in the way matter is arranged across distance. When many millions of galaxies are seen together, their distribution becomes evidence. The pattern itself becomes a source of knowledge. In this vast setting, ordinary matter appears as the luminous skin of a deeper structure. Stars shine, galaxies glow, gas reflects and emits light. Yet most of the mass that shapes the large framework does not shine in any direct way. Observations indicate that dark matter forms much of the gravitational foundation on which the visible universe grows. Dark energy, in turn, relates to the large-scale expansion of the universe and to the way that expansion changes with time. At the level of the cosmic web, both hidden components leave their presence in the spacing, clustering, and growth of structure across the sky. The largest features are so extensive that they resist ordinary imagination. A galaxy cluster, large as it is, does not stand alone. It belongs to a richer environment of neighboring clusters, connecting filaments, and surrounding emptier regions. A filament is a long, thread-like concentration of matter and galaxies stretching across enormous distances. A void is a broad region containing far fewer galaxies than average. Neither is truly empty or solid. Each is part of a continuous structure shaped by the history of expansion and gravity. Together they make a universe that resembles foam, lace, or branching roots only in the loosest visual sense. Such comparisons help the mind, but the reality remains more exact and more immense. This large-scale pattern develops gradually from small differences present in the early universe. Matter is not distributed with perfect sameness at the beginning. Slight variations in density exist. Over time, gravity amplifies those differences. Regions that begin slightly denser attract more matter. They become denser still. Regions that begin slightly thinner lose relative influence. As billions of years pass, a web-like architecture emerges. The result is a universe in which the largest visible forms are not built by design, but by accumulation, collapse, flow, and long gravitational patience. Euclid studies this architecture by surveying a vast portion of the sky with consistent depth and sharpness. From the perspective of the broadest region, the importance of this strategy is simple. A structure this large cannot be understood through a handful of narrow views. It requires a map wide enough to show connections. One cluster gains meaning when seen within a surrounding network. One empty region gains meaning when compared with neighbouring walls of galaxies. One patch of sky gains meaning when placed beside many others. Breadth is therefore not merely a technical choice, it is part of the science itself. The mission's early survey releases already show how rich this outer layer of the universe appears when viewed at scale. In only a small fraction of its planned map, Euclid records millions of galaxies. The number is striking, yet the deeper significance lies in arrangement rather than abundance alone. These galaxies are not scattered like dust on a flat surface. They gather into recognizable large-scale patterns. Chains, groups, concentrations, and open gaps appear again and again. Even where the eye sees beauty first, science sees geometry, statistics, and history written across space. At this widest level, the dark universe is not yet a matter of close detail. It is a matter of hidden influence expressed through visible order. Dark matter cannot be seen directly in Euclid's images, but its role enters through the way structure forms and holds together. Dark energy cannot be picked out as a glowing region or a distinct object, yet its influence belongs to the history of cosmic expansion that determines how structure grows across time. The broad map of galaxies therefore serves as a meeting ground between the visible and the invisible. Light marks location, pattern reveals process, scale reveals law. This is why the mission carries quiet importance. It does not seek drama in rare events alone. It seeks coherence across enormous numbers. The dark universe becomes clearer not because one single object explains it, but because a wide survey compares countless objects and environments within one consistent framework. The strength of the method lies in repetition and relation. When similar patterns appear across different regions of the sky, confidence grows that the map traces genuine cosmic structure rather than local accident. The outermost view also places human observation in a modest position. A telescope near Earth surveys a sky that seems calm and two-dimensional to the eye. Yet that calm surface holds the record of a dynamic universe, extending over immense distances and ages. Every point of light belongs to a larger arrangement. Every apparent emptiness may be part of a giant void. Every crowded patch may sit along a filament or near a dense junction. The sky, when treated as a whole, becomes less like a scattered collection of separate sites and more like a single connected landscape. Within that landscape, Euclid reveals that the universe has shape on the grandest scales, and that this shape is one of the clearest entrances into the hidden majority of cosmic content. The mission opens with breadth. It shows that the widest map is not background. It is the first region of meaning, the outer face of a deeper reality expressed across the visible sky. After the larger structure of the universe is recognized as a connected pattern, the next region of understanding lies in the map itself, in the broad surveyed sky, and in the long span of cosmic time that such a map quietly contains. Euclid does not observe the whole sky. It selects a vast portion of it and measures that portion with a uniform method, a uniform depth, and a uniform level of sharpness. This decision gives the mission its scientific power. A survey becomes most useful when its observations can be compared across immense distances without the confusion that comes from mixing many different kinds of data. Consistency turns a collection of images into a coherent view of the universe. The sky, as seen from Earth, appears as a dome of light and darkness spread overhead. In astronomical work, that dome becomes a measurable surface. Positions are marked with precision. Areas are counted. The whole celestial sphere can be divided into regions suitable for systematic study. Euclid surveys a very large area, wide enough to include an enormous range of cosmic environments. Some lines of sight pass through crowded regions rich in galaxies. Others pass through sparser regions where the visible matter thins out. Taken together, these many directions form a broad statistical field. The mission does not depend on a single remarkable object. It depends on the measured character of the sky over a great expanse. This surveyed region is valuable not only because it is wide, but because it also reaches deep into time. In astronomy, looking far away means looking into the past. Light requires time to travel. The farther a galaxy lies from the observer, the longer its light has been on the way. A telescope that records galaxies across a great range of distances is therefore recording many different stages of cosmic history at once. Nearby galaxies show the more recent universe. Distant galaxies show earlier conditions. The sky becomes a layered record of time, spread across distance but received together in the present moment. Euclid's survey joins these two dimensions, breadth across the sky and depth through time. This combination is essential. A narrow but deep view can reveal very distant galaxies, yet it may fail to show how those galaxies relate statistically to the wider cosmic pattern. A wide but shallow view can show distribution across large angles of sky, yet it may miss much of the distant history needed to trace change over time. Euclid stands in the middle of these requirements. It seeks a map large enough to capture structure on grand scales and deep enough to follow that structure across a large fraction of cosmic history. In this way, the mission treats the sky not as a flat surface, but as an entrance into a time-filled volume. Every measured direction contains galaxies at different distances. Every distant source adds a past moment to the survey. The result is not a simple photograph of what exists now in one cosmic instant. It is a carefully assembled census of light arriving from many ages. That is one reason the map has unusual scientific richness. It allows researchers to examine not only where matter appears to be distributed, but also how that distribution differs between earlier and later eras of the universe. This temporal depth matters because dark energy is not inferred from a single location. It is connected to the history of cosmic expansion. Dark matter also leaves its strongest evidence not only in isolated structures, but in the way structure grows through time under gravity. A survey that stretches across both sky and history can compare regions and epochs within one common framework. It can ask how clustering changes. It can ask how the apparent arrangement of galaxies relates to the expansion of space itself. It can ask how the broad form of the cosmic web develops from earlier times toward the more recent universe. The practical meaning of this design becomes visible in the sheer abundance of objects the mission records. Even in its early results, Euclid observes many millions of galaxies in only a small fraction of its intended survey. This abundance is not simply impressive in scale, it is scientifically necessary. The hidden components of the universe are subtle in their effects. Their influence becomes clearer when measured across large populations. A small sample may mislead. A vast sample allows averages, patterns, and departures from expectation to emerge with greater reliability. The mission therefore builds knowledge through number, repetition, and uniform comparison. The surveyed sky also demands care in selection. Some parts of the sky are more suitable for a clean extragalactic view than others. Dust, stars, and other foreground features associated with the Milky Way can complicate observations if they dominate the line of sight. A broad cosmological survey must therefore emphasize regions where the distant universe can be seen with relative clarity. This is not a matter of seeking visually empty places for convenience alone. It is a matter of reducing contamination so that faint distant galaxies can be measured with consistent accuracy across a wide field. Seen in this way, the surveyed sky is neither arbitrary nor complete. It is purposeful. It samples enough of the celestial sphere to represent the large-scale universe while remaining suited to the exacting needs of precision cosmology. It balances breadth, depth, clarity, and repeatability. It creates a data set in which the same kinds of measurements can be applied again and again across a huge domain. That regularity is one of the quiet strengths of the mission. The dark universe does not reveal itself through spectacle. It reveals itself when measurements made in one region can be trusted against measurements made in another. Cosmic time within this map is not presented as a sequence of separate scenes. It exists as an ordered distribution of distances. The survey captures light that leaves galaxies long ago and arrives now. Each signal placed into a broader framework, the effect is gentle but profound. One part of the sky can contain evidence from relatively recent epochs, while another nearby point can contain evidence from a much earlier era, all within the same measured field. Space and time remain linked throughout the survey. The map is broad, but it is also deep with memory. Thus, the second region of the topic remains within the scale of the survey itself. It is the level where the sky becomes territory and distance becomes history. Euclid's map is large enough to be meaningful, deep enough to be historical, and uniform enough to turn a wide celestial field into a tool for studying the hidden framework of the cosmos. At this stage, the mission's achievement is not yet the close inspection of particular structures. It is the creation of a measured domain in which the visible universe can be compared across enormous extents of both space and time. Within the broad surveyed sky, some regions receive a different kind of attention. They're not separate from the main map, yet they are observed with added patience and repeated care. These are the deep fields. In the context of Euclid, a deep field is a selected region of sky that the mission returns to again and again, building a view that reaches farther and reveals fainter objects than a single ordinary pass can provide. The deep field remains part of the same universe and part of the same survey, but it becomes a richer window, one in which the density of visible cosmic history grows much thicker. A wide survey establishes scale and coherence. A deep field adds concentration. It allows the mission to linger within a chosen area and gather more of the faint light that would otherwise remain below the threshold of reliable detection in such a field. Galaxies that are too dim, too distant, or too small to stand out clearly in a shorter observation begin to emerge. What appears at first to be a modest patch of sky fills gradually with structure. More points of light become identifiable as galaxies. More galaxies reveal form. More form yields a fuller census of what lies along that line of sight. The value of a deep field does not lie in spectacle alone. Though the images can appear crowded and intricate, its value lies in concentration of information. A small region, carefully observed, contains galaxies at many distances and many stages of development. Light from relatively nearer systems mixes with light from much earlier eras. The field becomes thick with overlapping layers of time. Because Euclid returns to the same region repeatedly, it can build up the signal from faint objects and improve the statistical strength of what it records there. The result is not a different universe but a denser reading of the same one. This added depth matters because much of cosmology depends on large populations rather than a few bright examples. A deep field increases the number of galaxies visible within a given area. That increase supports studies of how galaxy populations vary with distance and environment. It strengthens the map of cosmic history by filling in regions of the observational record that are otherwise thin. It also helps the mission test and refine the methods used across the wider survey, since a deeper view can reveal what a shallower pass includes clearly and what it leaves incomplete. Euclid's early deep field results show this principle with unusual clarity. In a limited portion of its eventual survey, the mission records millions of galaxies in selected deep regions after only a short period of observation. The scale of that result is meaningful, not because the deep field stands apart from the rest of the map, but because it demonstrates how much information is packed into even a small piece of the sky when observed with precision and repetition. What seems small in angular extent becomes vast in content. The field is narrow compared with the survey as a whole, yet it contains an immense range of distance, brightness, and cosmic circumstance. In these regions, the sky no longer feels sparse, it becomes textured almost everywhere. Many of the visible sources are galaxies, each one a system of stars, gas, dust, and dark matter held together by gravity. Some are nearer and show clearer structure, others are more distant and appear smaller, fainter, and more delicate. Many belong to no immediate visual pattern at first glance, yet together they contribute to the broader statistical fabric from which cosmological conclusions are drawn. In a deep field, the abundance of these sources creates an impression of fullness. The universe, when observed long enough, reveals that apparent emptiness often reflects limits of observation rather than absence of content. This feature of deep fields also carries a quiet lesson about faintness. A distant galaxy is not necessarily small in reality. It often appears small because of distance and dim because its light has travelled so far. Repeated observations help recover part of that lost visibility. By gathering more light over time, the mission improves its ability to separate genuine distant sources from noise and to characterize faint objects more reliably. The deep field therefore acts as a place where the boundary of observation is pushed farther outward, not by changing the laws of nature, but by extending the act of measurement. Another strength of these regions lies in continuity, because they are embedded in the same overall mission design. The deep fields do not become isolated special cases detached from the main survey. They remain connected to the larger map through common instrumentation, common calibration, and common scientific purpose. This makes them especially useful. Their depth enriches the broader dataset instead of competing with it. They provide a concentrated record that can be compared with the wider, shallower coverage, helping astronomers understand completeness, refine source classification, and strengthen confidence in how the full survey is interpreted. The deep field is therefore both narrow and expansive at once. It is narrow on the sky, defined by a limited viewing area. It is expansive in what it contains, reaching across great distances and including a multitude of galaxies from different times in cosmic history. This dual nature gives it scientific elegance. A small chosen region becomes a heavy reservoir of information. It condenses the long record of the universe into a manageable observational frame while remaining part of a survey whose main ambition is breadth. There is also restraint in the way such fields are understood. They are powerful, but they are not treated as complete representations of everything on their own. One deep field, however rich, still samples only a limited direction through the cosmos. Its meaning grows when placed within the mission's much wider program. This is why the deep field belongs naturally to the surveyed sky rather than standing outside it. It is a deeper chamber inside the same mapped domain, a more concentrated interior within the larger observational shell. At this stage of the journey inward, Euclid's deep fields reveal how a broad survey can also become intimate without ceasing to be systematic. The mission pauses over chosen regions and allows hidden populations of faint galaxies to gather into view. It turns a small portion of sky into a densely layered archive of cosmic light. Within that archive, the dark universe remains unseen in any direct sense, yet the visible record becomes richer, fuller, and more capable of supporting the careful inferences on which the mission depends. Within the broad mapped sky and within the specially observed deep fields, the large-scale universe begins to separate into distinct environments. The cosmic web is not a uniform mesh. It contains regions of different density, different shape, and different gravitational history. At this level, the outer pattern becomes more detailed. The great web resolves into clusters, filaments, and voids. These are not decorative features laid across space. They are the main environments in which galaxies live, gather, and spread apart on the largest scales. Each one expresses how matter responds to gravity over immense stretches of time. A cluster is a dense gathering of galaxies bound together by gravity. It contains many galaxies in a relatively compact region compared with the surrounding large-scale structure. The galaxies within a cluster do not sit still. They move through the shared gravitational field, often at very high speeds. Between them lies hot gas filling much of the cluster volume, while dark matter provides most of the mass that holds the system together. The visible galaxies are therefore only part of the whole. A cluster appears to the eye as a crowded region, but in physical terms it is a deep gravitational basin in which several components coexist. Clusters are important because they are among the largest structures in the universe that remain gravitationally bound as single systems. Their existence shows where matter has gathered most strongly. Over long periods, denser regions attract more material from their surroundings. Smaller groups and surrounding matter streams contribute to growth. In this way, a cluster represents both an endpoint and an ongoing condition. It is the result of earlier accumulation, yet it also continues to evolve as galaxies interact. Gas moves, and the system responds to its own internal gravity. A filament is different. It is not a compact knot but an extended bridge or strand of matter, linking denser regions across large distances. Galaxies line these structures in elongated arrangements, and clusters often sit where several filaments meet. A filament has lower density than a rich cluster, yet it remains denser than the emptier regions around it. In the architecture of the cosmic web, filaments provide connection. They form the long frameworks along which matter is distributed. They give the web its thread-like appearance and help define the shape of the regions between them. Filaments are not rigid beams suspended in space. They are regions in which matter is more likely to be found because gravity has guided its distribution over time. Galaxies within filaments may fall toward denser nodes, may gather into groups, or may continue along the broader flow of structure formation. Gas also exists within and around these regions, though much of it can be difficult to detect directly. The filament therefore stands as a large-scale environment, quieter in appearance than a cluster, but fundamental to the way matter is arranged across the universe. A void is the contrasting environment. A void is a broad region where the number of galaxies is much lower than average. It is not perfectly empty. It can contain galaxies, gas, and dark matter, but all at significantly reduced density compared with the web around it. In the widest map, voids open like great hollow spaces between filaments and clusters. Their scale can be enormous. They occupy much of the volume of the universe, even though much of the visible matter is concentrated in the denser structures surrounding them. The emptiness of a void is not absolute absence, but relative scarcity. This distinction matters. A void is defined by comparison with the cosmic mean and with neighbouring structures. It is a place where matter has not gathered strongly. Over time, as denser regions attract more material, underdense regions become more underdense in relative terms. Matter tends to flow away from them toward the surrounding filaments and nodes. In this sense, a void is shaped by the same gravitational evolution that builds clusters. The difference lies in direction and density. One environment accumulates, another thins. These three environments are not isolated categories placed side by side. They belong to one continuous structure. A filament can feed a cluster. Several filaments can border a void. A void can expand in relative emptiness as matter gathers more strongly along its boundaries. The cosmic web is therefore best understood not as a set of separate objects, but as a connected landscape of differing density. Clusters are the deep nodes. Filaments are the connecting strands. Voids are the broad interior gaps enclosed by the network. Together they form the main habitats of large-scale cosmic structure. For Euclid, these environments are valuable because they carry the imprint of hidden mass. The visible galaxies mark where matter has collected, but they do not account for the full gravitational picture on their own. Observations indicate that dark matter helps shape the growth of all three environments. It strengthens the gravitational scaffolding in clusters, supports the broader mass distribution within filaments, and contributes to the contrast between dense and sparse regions across the cosmic web. The visible map is therefore a partial view of a deeper arrangement. Even at the level of environment, light traces only part of what is present. This is why the mission studies very large populations of galaxies across very wide areas. A single cluster can be impressive, but the scientific pattern becomes stronger when many clusters are compared. When filaments are traced across many regions, and when voids are identified statistically rather than by impression alone. The aim is not only to admire structure, but to measure its distribution, abundance, scale, and growth. Different environments respond differently to cosmic history. Their relative numbers and shapes become part of the evidence from which the dark universe is inferred. There is also a quiet balance in this arrangement. The densest places, though visually striking, occupy only a small fraction of the total volume. The emptier places, though less dramatic to the eye, dominate the spatial extent. Filaments lie between, giving coherence to the whole. The universe at this scale is therefore not defined merely by where the most galaxies are. It is defined by contrast among environments. Density and sparseness work together to produce form. What gathers and what thins are equally important to the final pattern. In this fourth region of the journey inward, the cosmic web becomes a set of recognizable habitats. Clusters show concentration, filaments show connection, voids show rarefaction. Each one is a large-scale expression of gravity acting over time, and each one contains information about the unseen mass that shapes the visible universe. Euclid reads these environments as parts of a single connected map, where the form of structure itself becomes evidence about what the cosmos contains. After the large environments of the cosmic web come into view, a quieter region of the subject opens within them. It is not made of clusters, filaments, or voids themselves, but of the light that passes through and between them, Euclid depends on this travelling light. The mission does not touch dark matter directly or isolate dark energy as a visible substance. Instead, it observes how light from distant galaxies reaches the telescope after crossing a universe filled with matter. At this level, the dark universe begins to reveal itself not through the objects that emit light, but through the space that light crosses on its way. In ordinary experience, light appears to move in straight lines. Across daily distances, this is a good description. In the large-scale universe, however, space is not simply an empty stage on which matter sits. Modern cosmology describes gravity as the shaping of space and time by mass and energy. When matter is present, the geometry of space is altered. This means that light travelling across great distances does not always follow the simple path that an unshaped emptiness would suggest. It follows the structure of space itself. Where gravity is stronger, the path can be deflected. This idea is subtle because nothing about the light itself needs to change its basic nature. The light still travels at its natural speed through space. What changes is the geometry through which it moves. A useful term here is curved space, meaning space whose shape is influenced by matter and energy, rather than remaining perfectly flat in a simple geometric sense. The phrase does not require an image of a visible surface bending like fabric in ordinary air. It describes the fact that distance, direction, and motion on cosmic scales are affected by gravity in a way that changes how light arrives from faraway sources. In the broad environment of the cosmic web, this matters deeply. A galaxy far from Earth sends light outward in all directions. Some small part of that light eventually travels toward the region of the solar system and reaches a telescope such as Euclid. Yet on its way, it may pass near concentrations of matter. It may cross regions associated with clusters or filaments. It may traverse more weakly populated space near voids. Each part of that journey occurs within a gravitational landscape. The light does not simply move across a blank emptiness. It travels across a shaped and structured universe. This means that the sky records not only the sources of light, but also the paths that light has taken. A distant galaxy appears in observation after its signal has crossed immense distances and encountered many gravitational influences along the way. The final image carries the history of that passage in a quiet form. The effect is often small, and in many cases it cannot be recognized by eye from a single object alone. Even so, the principle is powerful. Matter influences light even when that matter does not shine. This is one of the essential entrances into the study of dark matter, whose presence is known primarily through gravity rather than direct emission. At this stage, the subject remains general and spacious. The concern is not yet with particular categories of visible distortion, nor with rare dramatic cases. It is with the simple but far-reaching fact that the universe between source and observer matters. Distance alone does not define what is seen. Intervening structure also plays a role. A map of galaxies is therefore not just a record of where galaxies are. It is also, in a more indirect way, a record of how their light has crossed the shaped depths of the cosmos. The importance of this idea grows with distance. The farther a source lies, the more of the universe its light has crossed before arrival, over very short ranges. Such gravitational shaping may be negligible for most purposes. Over billions of years of travel, the accumulated influence of cosmic structure becomes significant. Light from distant galaxies encounters a long chain of environments, from relatively empty regions to denser concentrations of mass. The path may be altered gently rather than dramatically. but gentle changes repeated across immense datasets become scientifically meaningful. This is where Euclid's wide survey and high precision begin to meet each other. The mission observes huge numbers of galaxies, many at large distances, and records them with care sufficient to support the study of very subtle effects. The scientific promise lies in the combination. If space is shaped by matter, and if light responds to that shaping, then a precise map of many distant sources can reveal information about the matter that lies between them and the observer. Visible galaxies provide the light. Invisible matter contributes to the geometry. Observation joins the two. There is an important restraint built into this approach. Light does not provide a direct photograph of dark matter itself. The mission does not open a hidden window and show dark matter glowing in its own form. Instead, it measures consequences. The path of light becomes evidence. This distinction keeps the method sober and exact. Conclusions arise from careful inference rather than spectacle. The universe is read through its effects on visible signals, and those effects must be teased out with patience, repetition, and statistics. Curved space, then, is not a decorative idea added for abstraction. It is a practical part of how modern cosmology understands observation. Without it, the universe would appear simpler than it is, and the relationship between light and matter would be incomplete. With it, the sky becomes richer in meaning. Every distant galaxy is both a source of light and a probe of the space it has crossed. Every line of sight becomes a route through a gravitational landscape. The emptiness between galaxies becomes less like absence and more like a domain whose structure matters. In this fifth region of the journey inward, Euclid follows light across the large-scale architecture of the universe. The web of matter remains present, but now it is understood as a field that shapes paths as well as positions. The dark universe still does not appear directly. Instead, it enters through geometry, through travel, and through the quiet alteration of light by matter spread across cosmic space. Within the long paths that light follows across the shaped universe, one of the most delicate effects becomes especially important to Euclid. This effect is weak gravitational lensing. The term means the small change in the apparent shape and orientation of a distant galaxy caused by gravity from matter lying between that galaxy and the observer. The change is usually slight. It does not turn the sky into something visibly dramatic in ordinary inspection. Instead, it introduces faint patterns of stretching and alignment across very large numbers of galaxies. Those patterns can be measured, and from them the hidden distribution of mass can be inferred. The word weak matters here. It describes an effect that is subtle rather than overwhelming. A distant galaxy already has its own true shape, its own tilt, and its own structure. Some are rounder, some are longer, some are irregular. If only one galaxy were observed, its appearance would usually say very little about whether gravity along the line of sight has altered it. The natural diversity of galaxies is too large. Their forms vary on their own. The lensing signal becomes meaningful only when many galaxies are measured together. Then the random variety begins to average out, and a shared pattern starts to emerge. This is the quiet strength of weak lensing. It does not depend on a single striking case. It depends on collective tendency. If many distant galaxies behind the same broad foreground region appear stretched in slightly related ways, then the simplest explanation is that the intervening matter has influenced the light from all of them. The effect is small in each case, yet coherent across the population. That coherence turns subtle distortion into evidence. The sky begins to show where mass is concentrated, not because the mass shines, but because it nudges the appearance of background galaxies in statistically organized ways. The stretching itself is not like ordinary blur from a poor image. Blur softens detail without carrying a clear directional imprint from cosmic structure. Weak lensing produces something more disciplined. It can make galaxy images appear slightly elongated along preferred directions that relate to the gravitational field of the foreground matter distribution. The change may also affect apparent size and brightness in small ways. But the central power of Euclid's measurement lies in shape. It is the shape of many galaxies, compared carefully across wide areas, that reveals how the unseen mass is arranged. What matters most is that ordinary matter alone does not account for all the lensing signal expected across the sky. Visible galaxies mark some of the mass distribution, but observations indicate that much more mass exists in dark form. Weak lensing gives access to that broader mass field because gravity acts on light, regardless of whether the responsible matter emits radiation. In this way, the method treats light from distant galaxies as a probe and the intervening universe as the source of gentle distortion. The resulting map is not a map of brightness alone. It becomes a map of gravitational influence. A useful idea at this level is shear. Shear means a small stretching that changes shape more than size. In weak lensing studies, shear is the measured tendency for background galaxy images to lean away from their original random orientations and acquire a shared directional bias. Euclid seeks this signal across enormous numbers of galaxies. The individual distortions are tiny, but the average pattern across the sky can be traced with increasing confidence when the data set is large and the image quality is stable. Shear is therefore one of the main languages through which the hidden mass of the universe becomes measurable. This method places unusual importance on precision. If a mission aims to measure very small changes in shape, then it must observe with extraordinary consistency. The telescope, the detector, the optics, and the processing all need careful control, because any instrumental effect that imitates a cosmic stretching pattern would weaken the scientific result. Euclid is built with this demand in mind. It surveys the sky with sharp imaging and a stable observing strategy, so that the faint signal of weak lensing can be separated from the imperfections that every instrument naturally introduces. The science depends not only on seeing many galaxies, but on seeing them well enough that small distortions can be trusted. Weak lensing also has the advantage of scale. Because the effect is subtle and widespread, it can be studied across broad regions rather than only in rare places. This makes it especially powerful for cosmology. It traces mass on many scales at once, from denser regions associated with large structures to broader patterns spread across the cosmic web. When these measurements are compared across distances and across portions of the sky, they help reveal how structure grows with time. The hidden mass distribution becomes something that can be mapped statistically, not in perfect detail for every location, but with enough fidelity to test models of the dark universe. There is restraint in what weak lensing provides. It does not offer a simple picture in which dark matter appears as a visible object with clear edges. The inferred mass maps are the result of careful analysis, averaging, and reconstruction. They are meaningful because the underlying physics is well established, and because the measurements are repeated across very large samples. Yet the method always remains inferential. It converts slight, organized changes in the appearance of background galaxies into information about foreground mass. Its certainty grows from quantity, consistency, and agreement among many lines of analysis. This subtlety is part of the reason Euclid matters. A mission designed for weak lensing must combine broad coverage with strict image quality. It must gather enough galaxies for the signal to rise above randomness. It must measure their shapes with enough stability that tiny effects become detectable. It must preserve a coherent survey design so that one part of the sky can be compared reliably with another. The dark universe yields to this kind of patience. Its hidden mass does not announce itself directly. It leaves traces in the forms of distant galaxies, and those traces only become clear when the survey is both immense and exact. In this sixth region of the journey inward, the focus remains on the faint signature that gravity writes into light from faraway galaxies. Weak lensing turns the sky into a field of small distortions whose collective order reveals unseen matter. Through stretching, alignment, and statistical coherence, Euclid reads the hidden mass of the cosmos from the quiet reshaping of distant light. After the faint collective patterns of weak lensing, there is a rarer region in which the bending of light becomes easier to recognize. This is strong gravitational lensing. The underlying principle does not change. Light from a distant source still travels through a universe whose geometry is shaped by matter. Gravity still alters the path that light follows. What changes is the strength and clarity of the effect. In strong lensing, the mass lying along the line of sight is concentrated enough, and the alignment between source, intervening mass, and observer is suitable enough, that the distant light is bent into obvious forms. What appears in the image can include arcs, repeated images, and in special cases a near-complete ring. A strong lens is therefore a landmark. It is not important because it represents a different law of nature from weak lensing. It is important because it makes the same law easier to see. The invisible mass does not become visible in itself, yet its effect on background light becomes harder to miss. A single image may show a long curved arc where an ordinary galaxy image might otherwise have appeared. In another case, one distant source may appear in two or more places around a foreground mass. In a particularly symmetrical alignment, the light may form what is called an Einstein ring, a ring-like image produced when source, lens, and observer line up closely. The beauty of these systems can distract from their scientific discipline. The curves and rings appear elegant, yet they arise from gravity and geometry alone. A foreground concentration of matter, often a galaxy or a cluster of galaxies, acts as the lens. A more distant galaxy or other luminous source supplies the background light. The lensing mass bends the incoming light paths so that the observer receives them from altered directions. The telescope then records shapes and placements that do not correspond to the source in a simple one-to-one way. The resulting image is real light arriving by multiple curved routes through shaped space. The strength of the effect depends on both mass and alignment. A large mass bends light more strongly than a small one, but even a very massive system does not automatically produce a spectacular lens if the geometry is unfavourable. Strong lensing requires a relationship among source, lens, and observer that brings the bent paths into view in a clear manner. Because this geometry is relatively uncommon, strong lenses are much rarer than the subtle distortions used in weak lensing studies. Each one is a sharply expressed example of gravity at work on light across cosmic distance. Clusters of galaxies can produce especially dramatic cases. Their combined mass, including a large dark matter component, can bend the light from background galaxies into long arcs and multiple distorted images. A single cluster may act on many background sources at once, creating a scene in which light from the distant universe is folded and stretched around the foreground mass. In such systems, the visible galaxies in the cluster are only part of the lens. Much of the bending comes from mass that does not shine. Strong lensing therefore offers a powerful demonstration that the gravitational field of a system exceeds what its luminous matter alone would suggest. Individual galaxies can also serve as strong lenses. When a massive foreground galaxy lies nearly along the same line of sight as a more distant source, the light from the background object can be split into multiple images or wrapped into arcs around the foreground system. These cases are often smaller in scale than cluster lenses, yet they remain scientifically rich. They help astronomers estimate how mass, including dark matter, is distributed within and around the lensing galaxy. Euclid is well suited to the discovery of many such systems because it surveys a vast area with sharp imaging. Strong lenses are uncommon in any one small region of sky, but a mission that observes very large numbers of galaxies over wide fields has a much better chance of finding them in substantial numbers. This is one of the strengths of a wide cosmological survey. It creates the conditions under which rare but informative alignments can be identified across a large observational domain. In this way, Euclid can build a census of strong lenses rather than treating each example as an isolated curiosity. Such systems matter because they anchor interpretation. Weak lensing is subtle and statistical. Strong lensing is more conspicuous. The two belong to the same gravitational picture, but strong lenses provide especially clear cases in which the bending of light can be modelled with detail. The observed arcs, positions, and repeated images place tight constraints on the mass distribution responsible for the effect. The lens becomes a natural laboratory in which visible matter and hidden mass can be compared under the discipline of geometry. Gravity is shaping the light in a way that ordinary luminous matter alone does not fully explain. There is also a useful humility in strong lensing. However striking the image may be, it still does not show dark matter directly as a glowing ring or a separate shadow. The visible spectacle is the altered path of light from a background source. The hidden mass is inferred from the way that light is rearranged. This distinction keeps the method clear. The image is dramatic, but the reasoning remains controlled. An Einstein ring is perhaps the most elegant version of this process. When alignment approaches symmetry, the background light can appear wrapped around the foreground lens in a circular or near-circular form. The ring is not a physical hoop hanging in space. It is the image created by bent light arriving from many directions around the lens. Such systems are especially revealing because the geometry is strongly constrained. They show, in a single image, that space shaped by mass can redirect light into patterns that no ordinary straight-line picture could produce. In this seventh region of the journey inward, Euclid encounters the clearer landmarks of gravitational lensing. Arcs, repeated images, and rings stand out against the calmer background of ordinary galaxy shapes. These rare systems do not replace the quieter work of weak lensing. They illuminate the same physics in a stronger and more visible form. Through them, the hidden mass of the universe leaves one of its clearest signatures in the paths of light crossing cosmic space. After the clearer landmarks of strong lensing, the subject settles again into the ordinary visible population that fills Euclid's survey. These are the galaxies themselves. At this stage, they are not treated first as individual worlds of stars and gas, nor as separate histories of formation and change. They are treated as tracers. A tracer is something visible that marks a deeper pattern. In Euclid's work, galaxies serve this role across immense distances. They can be counted, located, compared, and grouped. Through their distribution, the broader arrangement of matter becomes measurable. This idea requires a certain restraint. A galaxy is a real physical system, not a mere dot placed for convenience on a map. It contains stars, gas, dust, and dark matter bound together by gravity. Many have long histories of growth, interaction, and internal change. Yet in cosmology, a galaxy can also be used in a more abstract way. It can act as a marker of place. When millions of galaxies are plotted across the sky and across distance, their positions begin to reveal the structure in which they reside. The visible systems become signposts of a larger framework. They do not trace that framework perfectly. This is an important part of the science. The visible matter in galaxies is only one portion of the total mass involved in cosmic structure. Dark matter extends beyond what can be seen in starlight. Gas between galaxies also contributes to the content of the universe. Even so, galaxies remain among the most practical and information-rich traces available to observation. They are bright enough to detect over vast distances, numerous enough to support statistics, and structured enough to be recognized with reliable methods across wide surveys. In this role, galaxies reveal clustering. Clustering means that galaxies are not spread evenly through space. Some are closer together than a random distribution would suggest. Others are farther apart. Groups, clusters, filaments, and walls emerge from these tendencies. When Euclid measures many galaxies under consistent observing conditions, it builds a map in which clustering can be studied with precision. The map becomes more than a catalogue. It becomes a record of how visible matter populates the cosmic web. This visible population has a strong relation to dark matter because galaxies tend to form and reside within dark matter halos. A halo is an extended concentration of dark matter, whose gravity helps gather ordinary matter and supports the formation of a galaxy, or a larger system. The dark halo does not shine, but the galaxy within it does. In this sense, the galaxy marks a place where the hidden mass has helped create a stable site of visible structure. The light therefore acts as a guide to a deeper gravitational setting. Yet galaxies are not identical traces. Different galaxies live in different environments and have different properties. Some are large and bright, some are faint and small, some are more common in denser regions, while others are found more often in less crowded settings. This means the visible galaxy population is shaped not only by the underlying matter field, but also by the history of galaxy formation. Cosmology must therefore be careful. A map of galaxies is not a direct photograph of all matter. It is a biased tracer in the scientific sense, meaning that the visible population follows the underlying matter in a systematic but not perfectly one-to-one way. This bias is not a flaw. It is part of what must be measured and understood. By comparing galaxy positions with lensing signals and with other statistical patterns, Euclid helps determine how visible galaxies relate to the broader mass distribution. In some places, the match is close in a broad sense. In others, the visible concentration may underrepresent or overrepresent the full mass pattern if judged by light alone. The science becomes richer when these relations are studied together rather than assumed to be identical. Galaxies are especially powerful tracers because they are abundant. A single galaxy carries limited cosmological meaning. A few galaxies reveal little about large-scale order. Millions of galaxies, spread across a vast survey, allow patterns to emerge with clarity. Dense regions can be identified. Correlations can be measured, statistical uncertainties can be reduced, rare environments can be compared with common ones. In this way, the humble act of recording where galaxies are located becomes one of the main tools for studying the dark universe. Their visible forms also help preserve order within the survey. A galaxy is not just a light source, it is a recognizable kind of source. It can be separated from stars in the Milky Way through its appearance and color. it can be classified with enough reliability to enter large samples. This practical point matters greatly in a mission like Euclid. The value of a tracer depends on correct identification. A survey seeking cosmic structure must know that it is mapping distant galaxies and not confusing them with foreground objects or with instrumental artifacts. The reliability of the tracer strengthens the reliability of the map. There is also a quiet elegance in the fact that the visible universe can be used in this way. The dark matter that shapes much of cosmic structure remains unseen directly, yet it leaves behind a luminous population that grows within its gravitational influence. The galaxies do not reveal the entire hidden architecture by themselves, but they illuminate it enough to make large-scale structure measurable. They serve as a readable layer placed within a deeper and darker framework. At this level of the journey inward, Euclid treats galaxies as coordinates of structure. They're light marks where matter has gathered strongly enough for visible systems to persist. Their collective arrangement reveals density, connection, and contrast across the surveyed sky. Their abundance allows statistical strength. Their limitations remind astronomy to remain careful. The map that emerges is therefore both direct and indirect at once. Direct, because the galaxies are truly observed. Indirect, because what they finally help disclose is larger than the visible systems alone. In this 8th region, the survey rests on a simple but powerful idea. The visible galaxies scattered across the sky are not only distant objects of light, they are traces of the deep gravitational pattern in which they exist. By following where they gather, where they thin out, and how they relate to hidden mass inferred by lensing, Euclid turns the ordinary galaxy population into one of its main guides through the dark universe. After galaxies are used as tracers across the wide map, the next inward region lies in how those tracers are placed in depth. A sky position alone is not enough. Two galaxies may appear close together when projected on the sky, and yet lie at very different distances. To understand the large-scale structure of the universe, astronomy must add depth to breadth. Euclid does this through redshift and distance. These do not give a direct physical line one can touch or see. They give a measured way of locating galaxies within the expanding universe and of turning a broad sky survey into a three-dimensional map. Redshift begins with light itself. White light can be separated into a spread of wavelengths, and astronomical sources often show patterns within that spread. Certain atoms and molecules absorb or emit light at characteristic wavelengths. When those patterns are observed in a distant galaxy, they do not always appear at the same wavelengths measured in a laboratory near Earth. In an expanding universe, the light travelling through space is stretched along with the expansion of space. Its wavelength becomes longer, because longer visible wavelengths move toward the red end of the spectrum. This stretching is called redshift. The term is simple, but its meaning is deep. A larger redshift usually indicates that the light has travelled from a more distant part of the universe and from an earlier time in cosmic history. Redshift is therefore not merely a colour effect. It is a measurable sign of cosmic expansion and a practical guide to distance. It allows astronomers to order galaxies in depth, rather than leaving them spread only across a flat celestial surface. Distance in cosmology is never entirely simple. The universe expands while light is travelling. The light reaching a telescope today has crossed a changing cosmic environment over a very long interval. For this reason, astronomical distance can be expressed in different related ways depending on what is being measured. Yet for Euclid's purpose, the central idea remains steady. Redshift gives a way to place galaxies along the line of sight and to compare nearer and farther populations within a consistent cosmological framework. It adds the third dimension that a sky image alone cannot provide. This step is essential because many of the mission's scientific goals depend on history as well as location. Dark energy concerns the expansion of the universe over time. Dark matter influences how structure grows over time. A map that shows only angular positions on the sky would miss this temporal dimension. By contrast, a map in which galaxies are sorted by redshift can show how clustering differs between earlier and later eras. The survey becomes a record of development rather than a single projected layer. Euclid approaches this measurement through both imaging and near-infrared observation. The mission records light in visible wavelengths with very high imaging quality, and it also observes in the near-infrared so that galaxies at greater distances can be characterized more effectively. The near-infrared is especially useful because the light from distant galaxies has been shifted toward longer wavelengths during its long journey across the expanding universe. Features that begin at shorter wavelengths can arrive in the near-infrared by the time they're observed. This helps the mission estimate or measure redshift across large galaxy samples. There are different levels of redshift measurement. In some cases, spectra provide especially direct information by showing how light is distributed across wavelength and where characteristic features appear. In other cases, carefully measured brightness through different filters can be used to estimate redshift by comparing how a galaxy's light is distributed across several wavelength bands. These methods differ in precision and in practical use, but both serve the same larger aim. They turn observed light into depth information. They convert the sky from a patterned surface into a structured volume. This volume is what allows Euclid to build a three-dimensional map of the cosmos. The phrase three-dimensional map does not mean that every galaxy is located with perfect certainty, like a point in an ordinary room. There are measurement limits, statistical uncertainties, and interpretive models involved. Even so, the map becomes genuinely three-dimensional in the scientific sense. It places galaxies not only across the sky, but also along the line of sight, ordered by redshift and therefore by cosmic distance and look-back time. Breadth and depth come together in one framework. The scientific value of this structure is considerable. Once galaxies are positioned in 3 dimensions, astronomers can measure clustering more faithfully. Structures that only seem connected in a flat image can be separated if their redshifts show that they lie at very different distances. Filaments and clusters can be studied with greater realism. Voids can be identified more accurately. The growth of structure can be compared across ranges of redshift, allowing the mission to test how cosmic expansion and gravitational growth relate to each other over time. There is also a quiet discipline in the use of redshift. It is not interpreted carelessly as a simple measure of motion through ordinary static space. In cosmology, redshift reflects the expansion of the universe itself and is read within an accepted model of cosmic geometry and history. This makes the measurement powerful, but also model-aware. Distance is inferred within a framework that has been built from many lines of evidence across modern astronomy. Euclid adds to that framework by bringing immense new data to the same broad questions. At this inward stage of the survey, the galaxies become less like points on a celestial chart and more like markers suspended through a deep cosmic volume. The map acquires thickness. A patch of sky that seems crowded may contain galaxies spread across many different epochs. A sparse-looking field may conceal substantial depth if its galaxies lie far away. Redshift reveals this hidden order. It allows the eye's flat impression to be replaced by a more faithful structure shaped by distance and time. In this ninth region of the journey inward, Euclid uses the stretching of light to measure the depth of the universe. Redshift turns light into distance and distance into history. The survey that begins as a wide view across the sky becomes a three-dimensional map of galaxies spread through cosmic time. Within that map, the dark universe can be studied not only as a pattern across space, but as a changing structure across the long expansion of the cosmos. After galaxies are placed across the sky and through depth, the next inward region lies in a quieter problem. The signal Euclid seeks in galaxy shapes is real, but it is small. A distant galaxy does not arrive at the telescope as a perfect geometric figure waiting to be read without difficulty. It arrives with its own natural structure, its own orientation, its own brightness pattern, and its own limits of visibility. On top of this, every observation carries the influence of the instrument, the detector, and the conditions of measurement. Before any conclusion about dark matter can be trusted, the mission must separate true cosmic distortion from the many ordinary sources of confusion that shape an image. This problem begins with the galaxies themselves. No two galaxies have exactly the same form. Some are broad and smooth, some are elongated, some are irregular, some show spiral structure. Others appear more compact or diffuse. Even without any gravitational lensing, the sky would contain a great diversity of galaxy shapes. This means that the image of one galaxy alone cannot usually reveal whether its form has been altered slightly by the passage of light through intervening mass. Its true unlensed shape is not known in advance. The natural variation of the galaxy population is therefore the first source of uncertainty. This intrinsic diversity creates a kind of noise. In science, noise means variation that obscures the signal being sought. Here the signal is the weak, coherent distortion caused by gravity along the line of sight. The noise is the fact that galaxies begin with many different shapes and orientations on their own. If enough galaxies are measured, their original orientations tend to average out statistically, while any shared lensing pattern can remain. But until that averaging is done with care, the natural variety of galaxies hides the delicate signal within a much larger field of ordinary difference. The next challenge comes from the telescope and its optics. No instrument forms a perfect image. Light passing through a real optical system is spread slightly, rather than focused into an ideal point. This spreading affects every observed object, especially faint and distant galaxies whose apparent sizes are already small. The result is a softening and reshaping of the recorded image. In astronomy, this instrumental response is often described as the point spread function, meaning the way the system records light from an ideal point source. If that response is not measured and corrected with great care, it can imitate or conceal the very stretching patterns Euclid is trying to detect. This is a demanding issue because the lensing signal is subtle. A tiny unwanted elongation introduced by the optics can matter greatly if the mission aims to measure tiny cosmic elongations in galaxy shapes. The task is not only to make sharp images, but also to understand exactly how the instrument modifies those images across the field of view and over time. A stable telescope helps, but stability alone is not enough. The behavior of the optical system must be characterized with precision so that the measured shapes of galaxies can be related back, as faithfully as possible, to the shapes of the incoming light before the instrument alters them. The detector adds another layer. A detector turns incoming light into recorded electronic data, but this process is not perfectly uniform in every pixel and every exposure. Small variations in sensitivity, charge movement, background signal, and readout behavior can influence the apparent form of faint sources. These effects are often subtle, yet in a mission devoted to shape measurement, subtle instrumental behavior matters. A survey like Euclid must therefore calibrate its detector response carefully, monitor it continuously, and account for its influence in the analysis. The dark universe can only be inferred reliably if the instrument's own fingerprint is kept under discipline. There is also statistical noise from limited light. A faint galaxy does not deliver an unlimited stream of photons. The recorded image is built from a finite number of detected light signals, and this introduces unavoidable variation. A brighter object can be measured more precisely because more light arrives. A fainter one carries greater uncertainty. Since Euclid surveys very large numbers of distant galaxies, many sources lie close to the boundary where measurement remains useful but not effortless. Their shapes can still contribute to the science, but only if their uncertainties are modelled honestly and their inclusion is handled with care. Crowding adds another difficulty. In regions where many galaxies appear close together on the sky, one source can affect the apparent boundary or brightness distribution of another. A faint galaxy near a brighter neighbour may be harder to isolate. Its shape may be partially blended with surrounding light. This blending is not a sign of cosmic lensing. It is an observational complication that must be recognized and corrected where possible. The deeper a survey goes, the more relevant this becomes, because the number of visible sources rises and apparent separations can shrink. At this level of the mission, the work becomes exacting rather than grand. The broad cosmic web remains the reason for the survey, but the immediate task is humble. It is the removal of error, imitation, and confusion. The hidden mass of the universe cannot be mapped from galaxy shapes unless those shapes have first been measured in a way that respects every known source of distortion unrelated to gravity. Precision becomes a form of honesty. It prevents the telescope from being mistaken for the cosmos. This is why Euclid depends on repeated calibration, careful image processing, and statistical methods designed for very large samples. The mission does not assume that raw images speak for themselves. It recognizes that every measurement is an encounter between the sky and the instrument. To learn about the sky, one must first understand that encounter. The shape of a galaxy in the data is partly cosmic and partly observational. The scientific task is to separate these parts without overstating certainty. There is a quiet elegance in this stage. The farther inward the inquiry moves, the less it resembles a simple act of looking, and the more it becomes a disciplined act of interpretation. A successful shape measurement does not come from seeing only more galaxies. It comes from understanding how every part of the observing system interacts with faint distant light. When that understanding is strong enough, the weak lensing signal can emerge from beneath the ordinary disorder of natural shape variation. Instrumental blur, limited light, and crowded fields. In this 10th region of the journey inward, Euclid confronts the boundary between image and inference. The mission must distinguish true cosmic distortion from the many ordinary effects that alter what a galaxy seems to be. Only by controlling noise, blur, and measurement uncertainty can the survey turn faint changes in shape into reliable evidence about the hidden mass of the universe. After the survey has been understood in terms of structure, light, shape, depth, and measurement, the next inward region lies in the observatory's place in space. Euclid does not work from the surface of Earth. It observes from a distant gravitational region known as the Sun-Earth Lagrange point 2, often called Lagrange 2 or L2. This location lied about 1.5 million kilometers from Earth, in the direction away from the Sun. It is not a solid destination or a fixed platform. It is a special region in the Sun-Earth system where orbital motion and gravity combine in a way that makes long-duration astronomical observing especially effective. A Lagrange point is a place where the gravitational pull of two larger bodies and the motion of a smaller body can create a useful balance. In the Sun-Earth system, there are several such regions. Lagrange 2 lies beyond Earth on the night side direction, along the line joining Earth and the Sun. A spacecraft placed there does not sit motionless like an object resting on a shelf. It continues to orbit the Sun along with Earth. The importance of the region is that it keeps the spacecraft in a favorable geometric relationship with both Earth and the Sun, while requiring only modest orbit maintenance compared with many other possible observing locations. Euclid does not remain at an exact mathematical point. Instead, it follows a wide path around the Lagrange 2 region, often described as a halo orbit. This means the observatory loops around the region in a large three-dimensional path rather than trying to occupy a single ideal position. Such a path gives operational and thermal advantages and allows the spacecraft to maintain a stable observing configuration. The orbit is graceful rather than dramatic. It is a continuous controlled motion suited to a mission whose main strength lies in steadiness, repetition, and wide survey coverage. This location matters first because it offers a quiet thermal environment. A telescope that measures faint galaxy shapes and delicate signals in the dark universe must remain extremely stable. If the observatory warms and cools too strongly or too irregularly, its structure can expand and contract in small ways that affect image quality and measurement precision. At Lagrange 2, Euclid can keep the Sun, Earth, and Moon in roughly the same general direction. This makes shielding simpler and helps the spacecraft maintain a more constant thermal state. Stability of temperature supports stability of the optics and the detectors, and that stability supports the scientific goal of precision. The observing environment is also quieter in another sense. Near Earth, a spacecraft in low orbit repeatedly passes in and out of sunlight and shadow. It also sees Earth fill a large part of the sky, bringing changing heat and stray light conditions. Those repeated environmental changes complicate precision observation. At Lagrange 2, the geometry is calmer. The spacecraft remains far from Earth, and the bright bodies that most affect heating and illumination stay gathered within a more limited part of the sky. This does not remove every operational challenge, but it greatly reduces the rhythmic disturbances that a lower orbit would impose. For a wide cosmological survey, this calm matters deeply. Euclid is not built to chase short-lived explosive events across the sky. It is built to perform a uniform program of repeated, careful measurements over a long time. Its work depends on consistency from one field to the next, and from one season of observation to another. A stable orbit supports that consistency. When the environment is predictable, the images become more comparable. The instrument behavior becomes easier to model, and the mission can preserve the coherence that a dark universe survey requires. Lagrange 2 also supports a favorable view of the sky. The observatory does not see every direction at every moment, because its orientation must respect thermal and power constraints. Yet the geometry of its location allows access to a very large observing domain over the course of the mission. The sky can be surveyed systematically rather than opportunistically. This suits Euclid's method. The mission advances through many carefully planned pointings, building a broad and uniform map rather than collecting disconnected scenes. Its place in space is therefore part of its survey logic. The orbit is not only where the spacecraft happens to be, it is part of how the science becomes possible. Communication with Earth also remains practical from this region. Although Euclid is far away compared with Earth-orbiting satellites, it is still close enough for regular contact and mission operations. Data can be returned, commands can be sent, and the observatory can be monitored and guided through its long program. The distance is large in human terms, yet manageable in the scale of space astronomy. This balance between remoteness and operability is one reason Lagrange 2 has become important for sensitive space observatories. There is a certain elegance in this arrangement. Euclid studies the largest structures in the universe, yet it does so from a location chosen for environmental quiet, rather than dramatic proximity to any particular object. The mission goes outward from Earth in order to create inward stability. It leaves the crowded thermal and optical influence of near-Earth conditions so that its measurements of distant galaxies can become more exact. The observing site does not add spectacle to the survey, it removes disturbance. This region also reflects the broader character of modern cosmology. The great questions concern dark matter, dark energy, and the growth of cosmic structure over billions of years. Yet progress toward those questions often depends on practical matters of orbit, temperature, pointing, and stability. A spacecraft at the wrong location would still see the sky, but it might not see it with the uniformity required for a survey like Euclid. The choice of Lagrange 2 therefore links engineering and science in a direct way. Precision cosmology begins with a quiet platform. In this 11th region of the journey inward, Euclid is understood as an observatory held in a favourable gravitational neighbourhood beyond Earth. Lagrange 2 gives the mission distance from terrestrial disturbance, a steadier thermal setting, and a geometry well suited to long systematic observation. From that calm orbit, the spacecraft can carry out the patient work of mapping the visible traces of the dark universe with the consistency that such a task demands. After the observatory's quiet place in space is established, the next inward region lies inside the telescope itself, where incoming light first becomes organized for measurement. Euclid studies the dark universe through the visible light of distant galaxies. Yet before that light can become a map, it must pass through a carefully designed optical system. At this level, the mission is no longer defined by the broad sky, by cosmic structure, or by the spacecraft's orbit. It is defined by the path a beam of light takes after entering the telescope. The scientific goal remains the same, but the setting becomes more intimate. The concern is now with collection, reflection, guidance, and separation. A telescope begins with a simple purpose. It gathers more light than the human eye can gather, and brings that light into a controlled form so that faint distant sources can be measured. In Euclid, this gathering is done by a mirror system rather than by a large simple lens. Mirrors are well suited to astronomy because they can collect light efficiently, avoid certain optical problems associated with lenses, and direct the beam through compact folded paths inside the observatory. When light from a distant galaxy reaches Euclid, the wavefront arriving at the spacecraft is extremely faint, yet it still carries information about shape, brightness, colour, and structure. The telescope's task is to preserve that information as faithfully as possible. The first main element in this process is the primary mirror. This is the large collecting surface that receives the incoming light and reflects it inward through the optical system. Euclid's primary mirror has a width of about 1.2 meters. This size allows the observatory to gather enough light from very distant galaxies while maintaining a design suitable for the stable space environment in which the mission operates. The mirror does not magnify in the simple everyday sense. Its deeper role is to gather faint light over a broad area and redirect it with precision. A distant galaxy sends only a tiny amount of its light toward the telescope. Without a collecting mirror of substantial size, much of that faint signal would remain beyond useful measurement. Reflection is central here. A mirror changes the direction of incoming light while preserving its optical content more effectively than a thick transmissive element would under comparable conditions. The surface must be shaped with extraordinary care so that rays arriving from the same distant source are brought into a controlled optical relationship rather than scattered unpredictably. Even tiny surface errors matter. A mission like Euclid depends on image sharpness and stability, especially because the shapes of galaxies must be measured with very high precision. The primary mirror is therefore both a light collector and a guardian of accuracy. The light does not stop there. After the primary reflection, it continues through additional optical elements that refine the beam and guide it toward the scientific instruments. Euclid uses a multi-mirror arrangement in which the beam is folded and corrected to provide a wide field of view with high image quality. This kind of design allows the observatory to record many galaxies across a large area of sky while maintaining the sharpness needed for weak lensing science. A wide field and high precision rarely come easily together. The optical path exists to make that combination possible. At this stage, the light remains unified. It contains visible wavelengths and near-infrared wavelengths together, all arriving from the same distant sources. Yet Euclid does not send this combined beam unchanged to a single detector. The mission needs different kinds of measurements from different parts of the light. For that reason, the beam is divided inside the telescope. This division is one of the most important inward transitions in the observatory. The same incoming cosmic light is separated into two paths so that two complementary scientific views can be obtained from the same sky. The splitting is done by an optical element designed to treat different wavelengths differently. A useful term here is dichroic, meaning a component that reflects some wavelengths while transmitting others. In Euclid, such a divider allows visible light to follow one route, while near-infrared light follows another. This is not a crude sorting process. It is a precise optical decision built into the architecture of the telescope. The incoming beam, gathered from extremely distant galaxies, is separated according to wavelength so that each part can be measured by the instrument best suited to it. This separation has quiet scientific elegance. The visible part of the light is especially valuable for sharp imaging of galaxy shapes. The near-infrared part is especially useful for extending observations toward more distant galaxies and for supporting the determination of their placement in cosmic depth. Both types of measurement begin with the same sources in the same sky. The telescope, therefore, does not observe two different universes. It takes one incoming stream of cosmic information and directs its different wavelength ranges along different routes so that more can be learned from each observation. The beam split also supports efficiency. A space mission devoted to a wide cosmological survey must make the most of every pointing. If visible and near-infrared information can be obtained within one coordinated optical design, the survey becomes more powerful and more coherent. The same region of sky can yield both precise shape information and the wavelength-based information needed for depth and classification. The optical system thus acts not merely as a collector of light, but as an organizer of scientific purpose. It decides how the sky is transformed into usable data. This inward region also reveals how closely the mission depends on order. Light from galaxies begins its journey across billions of years of cosmic expansion and gravitational structure. By the time it enters Euclid, it has already crossed a shaped universe. Inside the telescope, that light must cross another carefully shaped world, one built by engineering rather than gravity. Mirrors, angles, coatings, and optical surfaces now determine whether the information survives in a form precise enough for cosmology. The telescope becomes a kind of final passage through which ancient faint light is prepared for measurement. There is no spectacle in this process when viewed physically. Nothing explodes into colour inside the observatory. No hidden substance is exposed. The action is quiet and exact. Light enters, reflects, narrows, folds, and separates. Yet this controlled sequence carries great consequence. Without it, the broad map of the dark universe would remain unattainable. The cosmic web, weak lensing, and the measurement of distance all depend on this interior discipline of the optical path. In this 12th region of the journey inward, Euclid's work passes from space into optics. The telescope gathers faint light with its primary mirror, guides that light through a carefully corrected path, and then separates visible and near-infrared wavelengths into distinct routes. One beam becomes two, not because the sky is divided, but because the mission needs different readings of the same distant universe. Inside this quiet optical structure, the ancient light of galaxies is prepared for the measurements on which the dark universe can be studied. After the light has been collected and separated inside the telescope, the next inward region lies along the visible route, where Euclid measures the fine outlines of distant galaxies with great care. This region belongs to the visible camera, the instrument designed to record sharp images across a wide field of sky. In Euclid, this instrument is known as vis. Its task is quiet but exacting. It does not search for spectacle in colour or dramatic variation in brightness. It records shape. That single word carries much of the mission's weight at this level, because the shape of a distant galaxy holds the faint imprint of the gravitational path its light has crossed. A visible camera in astronomy is not merely an ordinary camera placed in space. It is an instrument built to preserve spatial detail with unusual stability across a very large field. For Euclid, this matters because weak gravitational lensing alters galaxy shapes only slightly. A mission seeking that signal cannot rely on rough images or on broad impressions. It must record the outlines of galaxies cleanly enough that very small statistical distortions can be measured across millions of sources. The visible camera therefore becomes one of the mission's most disciplined tools. It turns incoming visible light into a data set in which form can be examined with precision. The visible route is valuable because shorter wavelengths can support especially fine imaging when the optics and detector are designed well. In practice, this means Euclid can record the apparent structure of galaxies with the sharpness needed to estimate their ellipticity, their degree of elongation, and the orientation of that elongation on the sky. Ellipticity means how much a shape departs from being round. It is a practical quantity in weak lensing studies because gravitational shear often appears as a very small shift in the apparent ellipticity and alignment of many background galaxies. The visible camera is therefore built not only to see galaxies, but to see them in a way that makes their slight departures from roundness scientifically useful. This work depends on a wide field as much as on sharpness. A narrow instrument might record exquisite detail in a small region, yet Euclid must survey enormous areas of sky to obtain the statistical power required for cosmology. VIS is designed to do both at once. It observes a broad field while maintaining image quality suited to shape measurement across that field. This combination is not simple. Optical sharpness can vary from one part of an image to another, and detector behavior can differ across a large focal plane. The instrument's design therefore aims for uniformity as well as resolution. A galaxy near one part of the image must remain comparable to a galaxy recorded elsewhere if the survey is to preserve its scientific coherence. The detector system inside VIS is central to that goal. Incoming visible photons are converted into electronic signals by a large array of sensitive detectors. These detectors are arranged so that the focal plane covers a substantial area while preserving the fine sampling needed for galaxy shapes. The image is not made by a single surface acting in isolation, but by many detector elements working together in a coordinated system. Each one must respond predictably, because the mission depends on comparing galaxy shapes across the full field rather than only in a favoured central portion. This is why calibration remains so important within the visible camera itself. Even after the telescope optics have delivered a carefully prepared beam, the instrument must ensure that the recorded image is not misleading. Small effects in charge transfer, pixel response, background level, and readout behavior can all influence apparent shape. In everyday photography, such differences may pass unnoticed. In Euclid, they matter greatly. A very small instrumental preference for one direction over another could imitate a weak lensing signal if left uncorrected. VIS must therefore be characterized in detail so that its own structure does not masquerade as cosmic structure. The visible camera also serves the mission by reaching a large number of faint galaxies whose light is strong enough in the visible band to yield useful shape information. Not every detected galaxy becomes equally valuable for lensing analysis. Some are too faint, too small, or too blended with neighbours to support a robust measurement. Yet the survey is so wide and the instrument so capable that the remaining useful population is still immense. This is one of the quiet strengths of VIS. It does not need every galaxy to be perfect. It needs enough galaxies, recorded sharply and consistently enough, that the collective lensing signal can emerge above randomness and noise. Another key feature of the visible camera is stability over time. A survey mission unfolds across years, not moments. The shapes measured early in the program must remain comparable with those measured later. If the instrument's behavior drifts unpredictably, the science becomes harder to trust. VIS is therefore part of a long discipline of monitoring, recalibration, and careful control. Its value lies not only in single images, but in the repeatable character of those images across the whole mission. Weak lensing science depends on this continuity. The dark universe reveals itself through accumulations of precise measurements, and those measurements must remain tied to one consistent standard. There is also restraint in what VIS provides. It does not by itself measure all the properties needed for a complete cosmological map. Its special strength is shape. It records the visible form of galaxies with the clarity necessary for sheer analysis, helping astronomy infer how intervening mass alters the appearance of distant sources. It does not show dark matter directly. It does not isolate dark energy as a visible feature. Instead, it offers a stable visual record of galaxy shapes from which those hidden influences can be inferred when combined with the broader survey framework. At this inward stage, the mission becomes almost anatomical in its care. The broad universe has been reduced to the fine outline of one faint galaxy after another. Each shape is slight, each measurement is modest on its own, yet taken together, these many outlines form one of the mission's strongest paths into the dark universe. VIS gives Euclid the ability to treat visible light not merely as a source of pictures, but as a field of measurable forms whose tiny collective distortions can reveal the unseen mass between galaxies and the observer. In this 13th region of the journey inward, Euclid relies on the discipline of its visible camera. Vias records sharp galaxy images across a wide field, preserves their outlines with high stability, and provides the shape information required for weak lensing science. Through this instrument, the visible light of distant galaxies becomes a precise map of form, and form becomes one of the main ways the hidden mass of the cosmos can be studied. After the visible camera records the fine outlines of distant galaxies, the next inward region lies along the near-infrared route, where Euclid measures another part of the same incoming light. This region belongs to the instrument known as NISP, the Near-Infrared Spectrometer and Photometer. Its work complements the visible camera rather than repeating it. Where the visible route is especially important for measuring galaxy shapes. The near-infrared route helps place galaxies in depth, identify more distant populations, and extend the survey into wavelengths that become increasingly important as cosmic expansion stretches ancient light on its way across the universe. Near-infrared means light with wavelengths longer than visible red light, but shorter than the thermal infrared associated with heat radiation from warmer everyday objects. It remains part of the broader electromagnetic spectrum, yet it lies just beyond what the human eye can detect. For cosmology, this region is valuable because light from distant galaxies does not remain fixed at the wavelengths at which it was emitted. As space expands, the light is stretched. Features that begin in visible wavelengths can arrive shifted into the near-infrared by the time they reach the telescope. A mission seeking to study galaxies across deep cosmic time therefore gains important reach by observing in this range. NISP receives the portion of Euclid's light that the optical system directs along the near-infrared path. This light comes from the same galaxies already present in the wide survey and in the deeper fields. The instrument does not open a separate universe. It studies the same distant structures through a different part of their arriving signal. This is one reason the mission gains so much from its internal beam split. One route preserves sharp, visible shapes. The other route gathers wavelength information and sensitivity to more distant redshifted light. Together, they produce a fuller map than either could provide alone. The photometric side of NISP measures brightness through selected near-infrared bands. A band is a defined range of wavelengths recorded together. By comparing how bright a galaxy appears in different bands, astronomers can infer properties of its light distribution and estimate its distance in redshift space. This method does not rely on a single image alone. It relies on the pattern of brightness across several wavelength ranges. A galaxy at one distance will tend to place particular spectral features into one set of bands, while a galaxy at another distance will shift those features elsewhere. In this way, colour in the scientific sense becomes a guide to cosmic depth. The spectrometric side of NISP adds another level of information. A spectrum is the distribution of light across wavelength, spread out so that broad patterns and characteristic features can be studied in more detail. In Euclid, this is done in a slitless way, meaning the instrument disperses the light of many objects in the field without first isolating each one behind a narrow opening. This approach is well suited to a wide survey because it allows the instrument to gather spectral information for very large numbers of galaxies at once. It also introduces challenges, since spectra from nearby sources can overlap and must be disentangled carefully during analysis. Even so, the method offers an efficient way to connect wide area coverage with redshift measurement, The importance of the near-infrared grows with distance. Galaxies in the more distant universe send light that has been stretched more strongly during its journey. Features once emitted at shorter wavelengths move farther toward the red and into the infrared. A survey limited to visible light alone would gradually lose access to some of these signals or measure them less effectively. NISP helps prevent that loss. It keeps the survey sensitive to the receding light of remote galaxies and allows Euclid to build a more complete record of structure across cosmic time. This capacity is essential because the scientific questions depend on placing galaxies accurately within the expanding cosmos. A sky map without reliable depth would compress many different epochs into the same flat surface. The near-infrared measurements help separate those layers. They improve the mission's ability to estimate or measure redshift and thus to order galaxies by distance and time. This does not mean every galaxy receives the same level of precision, nor that every redshift is equally secure. There remain uncertainties, limits of signal, and challenges of interpretation. Yet the broad statistical strength of the survey depends on precisely this kind of wavelength-based depth information, and NISP is built to provide it. The instrument must do this work under strict conditions of stability and calibration. Near-infrared detectors have their own behavior, their own sources of noise, and their own sensitivity to thermal conditions. Because the mission operates from the quiet environment near Lagrange 2, the instrument can remain cold and stable enough to function as required for precision cosmology. Even so, careful calibration remains indispensable. Background levels, detector response, dispersive behavior, and source overlap all have to be understood if the resulting measurements are to serve the wider scientific goals. The dark universe cannot be studied reliably from raw infrared data alone. The data must be disciplined into trustworthy depth information. There is also an elegant complementarity between NISP and VIS. The visible camera measures shapes with great care, providing the statistical basis for weak lensing analysis. NISP adds the wavelength-based depth needed to place those shaped galaxies into cosmic time and three-dimensional structure. One instrument says where the slight distortions are, the other helps say how far away the sources lie and how the survey extends into earlier epochs. The two instruments therefore cooperate continuously. The same galaxy can contribute both a shape signal and a distance estimate, allowing the map of the dark universe to become both geometrical and historical. At this inward stage, Euclid's view becomes less like a picture and more like a measured distribution of light through wavelength. NISP turns faint infrared signals into estimates of distance, classifications of sources, and a stronger connection between what is seen on the sky and where it belongs in the deep expanding cosmos. It makes the survey more complete, especially for remote galaxies whose light has shifted beyond the visible range. Without this instrument, the mission would still see much, but it would lose a crucial part of the depth that turns observation into cosmology. In this 14th region of the journey inward, Euclid relies on its near-infrared instrument to follow the red-shifted light of distant galaxies and to transform that light into depth. NISP measures brightness across infrared bands and gathers spectra across wide fields, allowing the survey to reach farther into cosmic history and to place galaxies more securely within the three-dimensional structure of the universe. After the light has crossed the cosmic web, after galaxies have been mapped across the sky and placed through depth, after shapes have been measured and wavelengths recorded, the final inward region lies in interpretation itself. This is the stage at which Euclid turns immense collections of observations into cosmological evidence. The mission does not discover dark matter or dark energy by direct sight. It arrives at them through comparison, reconstruction, and statistical inference. At this level, the dark universe is approached not as an image, but as a pattern of agreement and tension between measured data and physical models. Statistics is the natural language of a survey like Euclid because the effects it seeks are distributed across huge numbers of sources. One galaxy shape carries little certainty. One lensing signal is too small to stand alone. One estimate of distance is useful, but limited. The power of the mission comes from combination. Millions of galaxies, measured under consistent conditions, can reveal collective behavior that no single source could establish. The large-scale clustering of galaxies, the weak lensing shear field, the abundance of strong lenses, and the distribution of galaxies through redshift all become meaningful when treated as populations rather than isolated cases. A statistical pattern is not vague by nature. In science, it can be highly precise when the sample is large and the measurements are controlled. Euclid uses this strength. It examines how often galaxies appear near one another at different scales, how their shapes show correlated stretching across the sky, how these effects change with redshift, and how the observed structures compare with theoretical expectations. Each of these measurements describes part of the same universe. When they are analyzed together, they place strong constraints on the invisible components that shape cosmic structure and expansion. Dark matter enters this stage through gravity. The mission's maps of lensing and clustering can be compared with models in which matter is distributed in different ways. If the visible matter alone is used, the observed growth and lensing of structure do not match what is seen. Observations indicate that a much larger amount of non-luminous matter must be present. Euclid does not identify the microscopic nature of that matter. It does not determine what particle it is, if it is a particle at all. What it can do is measure how much unseen gravitating matter is required, and how that matter appears to be distributed across scale and time. Dark energy enters through expansion and growth. The large-scale arrangement of galaxies and the history of structure formation depend on how the universe expands over billions of years. If expansion changes in one way, structures grow at one rate. If it changes in another way, growth is altered. Euclid studies this relationship by combining geometry and structure. Geometry comes from the mapping of distance and redshift across cosmic space. Structure comes from the distribution and lensing of matter across that mapped volume. Together they allow the mission to test how the expansion history of the universe relates to the formation of large-scale structure. This is why the mission has such broad design coherence. Every earlier region contributes to this final stage. The surveyed sky provides the scale. The deep fields enrich the census. The cosmic web provides environmental contrast. Light traveling through curved space enables lensing. Weak lensing gives access to the mass field. Strong lensing offers clear landmarks. Galaxies trace the visible structure. Redshift adds depth and time. Shape measurement controls the signal. The quiet orbit, the telescope, the visible camera, and the near-infrared instrument all preserve the conditions required for reliability. By the time the analysis reaches dark physics, every layer of the mission has already prepared the ground. The inference remains disciplined. Euclid does not prove more than the data allow. If the measurements agree with the current broad cosmological model within uncertainty, That agreement becomes a stronger test of the model's parameters. If tensions appear, they must be examined carefully to determine whether they arise from statistics, instrumental systematics, astrophysical complexity, or genuine new physical information. Precision does not remove uncertainty. It gives uncertainty a clearer shape. This is one of the deepest values of the mission. It narrows what can reasonably be true without claiming certainty where the evidence remains incomplete. A model in cosmology is not a guess in the casual sense. It is a structured mathematical description of how matter, energy, gravity, and expansion behave. Euclid compares observations with such models in order to constrain the values of the quantities that describe the universe. These may include the present amount of matter, the balance between ordinary matter and dark matter, the behavior associated with dark energy, and the way structure grows with time. The strength of the mission lies not in naming these quantities alone, but in refining them through independent observational channels that should agree if the model is sound. This cross-checking matters greatly. A single method can mislead if hidden bias remains in the data or in the interpretation. But if galaxy clustering, weak lensing, and redshift-based structure measurements all point toward the same general cosmological picture, confidence grows. If they disagree in a persistent and statistically meaningful way, then the disagreement itself becomes scientifically valuable. It may signal unresolved measurement issues, or it may suggest that accepted models need revision. Euclid is therefore not only a mission of confirmation, it is also a mission capable of exposing limits in present understanding. There is a quiet philosophical depth here, though the science remains practical. Most of the universe does not shine in the form humans can see directly. Much of what determines cosmic fate and structure is inferred through its effects. Euclid accepts this condition and works within it. The mission does not ask the universe to become simpler or more visible than it is. It develops methods suited to a cosmos in which hidden content still leaves measurable traces. This is a mature form of observation. It trusts patterns, agreement, and physical consequence more than direct visual familiarity. At the most inward point of this journey, the dark universe becomes a problem of disciplined reading, ancient light. After travelling across shaped space, enters a stable observatory, passes through mirrors and instruments, becomes calibrated data, and is then gathered into immense statistical structures. Those structures are compared with physical models of matter, gravity, and expansion. Out of that comparison comes not spectacle, but constraint. Not revelation in a sudden dramatic sense, but a gradual sharpening of what the cosmos permits. Euclid reveals the dark universe by reducing uncertainty, by measuring hidden influence, and by turning vast populations of galaxies into evidence about the deepest large-scale workings of the universe. The survey comes to rest in a quiet understanding. The dark universe does not become bright at the end. It remains largely unseen, yet less unknown than before. Across a wide portion of the sky, Euclid gathers faint light from distant galaxies and arranges that light into a patient record of structure, depth, and change. What first appears as scattered points becomes a connected map. What seems empty between galaxies becomes part of the story. What cannot be seen directly still leaves shape, alignment, clustering, and distance as steady forms of evidence. In this way, the mission does not remove mystery. It gives mystery clearer boundaries. It shows that the largest structures in the cosmos grow within a hidden framework of gravitating matter. It shows that cosmic expansion belongs to a history that can be measured with increasing care. it shows that precision, repeated over immense numbers of galaxies, can turn delicate signals into knowledge. The result is not a final answer to every question about dark matter or dark energy. Observations indicate more than was known before, yet it remains uncertain which deeper physical explanation will ultimately account for all that the data reveal. Still, the broad picture settles into calm form. Light travels for billions of years, space expands, gravity shapes the paths of that light and the growth of structure. Galaxies gather along filaments, collect in clusters, and thin around vast voids. A quiet observatory far from Earth records their outlines and their stretched wavelengths. From those measurements, the hidden architecture of the cosmos becomes more readable. The night sky then appears a little different, not fuller in brightness, but fuller in meaning. Its distances hold memory. Its patterns hold weight. Its darkness is not blankness, but depth. Euclid moves through that depth with patience, and from patience it draws a gentler clarity about the great unseen portion of the universe,